Tape recording uses electromagnetic induction to convert an electrical audio signal, a voltage, into magnetism, which is then used to realign magnetic particles on a reel of recording tape, creating a magnetic representation of the audio waveform. To play back the recorded signal, the reverse is done. The magnetic signal on the tape is converted back into an electrical waveform, again a voltage, which is then sent to the audio console for mixing and processing. Multi-track tape recorders do this independently for every track. Analog recording tape contains magnetic ferric oxide particles suspended in a slurry of chemicals and binders. The audio signal, the voltage to be recorded, is sent to the tape recorder where it's routed to the record head. This is basically a temporary magnet, or in the case of a multi-track recorder, a stack of independent magnets, one for each track. The record head converts the incoming voltage for a particular track into lines of magnetic force, or magnetic flux. The tape is pulled past the record head through the magnetic flux from the head, which forms at the gap of the magnet for a track in the record head. This magnetic field realigns the particles on tape to correspond to the positive and negative swings of the audio voltage, the audio waveform, creating a magnetic version of that waveform across the length of the tape. After the tape passes through the magnetic flux from the record head, the realigned magnetic particles retain their realignment. This is the actual recording, a magnetic representation of the audio wave, which has been permanently applied to the tape. The magnetic particles consist of domains. On a blank tape, these are randomly oriented, but as the tape is magnetized by the record head, they're reoriented to follow the polarity swings of the incoming magnetic flux, the incoming audio signal. The degree to which these particles retain the new magnetic state depends on the strength of the incoming signal. Weaker signals will realign only some domains, or a correspondingly lower recorded signal level. Stronger signals will magnetize more domains. When all the domains are magnetized, the tape is saturated. Higher incoming signal levels will not be reflected in the recording signal, gently clipping or distorting it at higher audio levels. Excess tape saturation is technically a flaw, but in small amounts it can add a little analog warmth and presence to the signal, and this effect, if managed carefully, is a part of the appealing sound of analog tape. To reproduce, or play back, a magnetic recording, the magnetized tape is pulled past another head, the repro, or playback head. As the magnetized particles on tape pass this head, the magnetic flux from the tape is converted back into a varying voltage. This signal is then sent to an amplifier or mixer for playback or mixing and processing. Since the changing magnetic signal is recorded across the length of the tape, the actual length of the magnetic version of the waveform depends on the speed at which the tape is pulled past the heads. Tape speeds are measured in IPS, inches per second. For professional recordings, the standard speeds are 15 IPS and 30 IPS. Smaller or semi-pro recorders might operate at 15 or 7.5 IPS. 30 IPS provides the best high-frequency response and greatest freedom from audible dropouts, but eats up a lot of expensive open-reel tape, especially in multi-track recording, and requires more robust motors and mechanicals to handle the tape at the higher speed reliably. 15 IPS is a good alternative and offers slightly better low-end response. To make good quality recordings, analog tape recording needs to be a linear process. The incoming waveform must be accurately magnetized on tape and reproduced in playback. However, the process is inherently not linear. A perfect transfer characteristic would be graphed as a diagonal line, as you can see. But when saturation occurs with stronger signals, the response is, of course, nonlinear. Naturally, this can be avoided by simply preventing signal levels from exceeding the saturation point. Less obvious is the inherent nonlinearity of lower-level signals. When the audio signal is strong enough, recording linearity is achieved, but due to the inertia of the magnetic medium, weaker, lower-level signals may fail to magnetize enough domains, resulting in an inaccurate representation of the signal at low levels, which alters the waveform, creating undesirable third harmonic distortion. To remedy this, an inaudible, high-level, ultrasonic, high-frequency signal is recorded on the tape along with the audio signal. This is called the bias frequency. The combination of the weaker, low-level audio signal and the stronger, inaudible bias signal provides strong enough magnetic flux to allow for linear recording of the low-level audio, reducing the otherwise objectionable third harmonic distortion. The actual level of the bias signal applied is a trade-off. The optimum level for minimal distortion may cause the high frequency response to fall off, so the bias level is set for the best balance between those two considerations based on the tape speed and formulation in use. We'll see how to make this over-bias setting when I cover the tape alignment procedure a little later in the course. Next up, a little more detail on the tape heads